Thank you. Now, I moved here a year ago to Kigali from Germany. And as the people in this room will certainly know, Germany shut down all of its nuclear power plants for purely political reasons. And this serves as an example. Nuclear cannot just be about the technology. We need to have cross-sectional discussions with policymakers, with regulators, for this technology to succeed. This is why I'm so glad to the Iranian Atomic Energy Board that they organized this vital summit. Here we can have the discussions that will allow this industry to move forward and deliver on its potential. I also want to thank His Excellency, President Paul Kagame, for allowing me my very own personal nuclear energy dream here in this country and pursue truly sovereign nuclear energy development that can enable energy security. I want to invite now the founder of Exafuse for his talk. Please welcome to the stage Christopher David Scott.
Okay, good afternoon. We're going to change it up gears a little bit. I'm Chris Scott, I'm founder of Exafuse. We're a small group of researchers and experimentalists distributed over the globe, and we would like to introduce a revolutionary thorium fuel concept. We've spent the last 12 months diligently checking our evidence to back up the claims that I'm about to make. You can go and find the detailed information at hyperpower.com. Look at the research presentations. I'm not going to be going into the detail needed to back those claims up in this presentation, but I want to give you the overview. Okay, the wild and maybe controversial claim is that we can enhance thorium's natural decay. Thorium is abundant throughout the globe, throughout Africa. The problem with thorium is it's lazy. It takes for each atom 14 billion years to undergo a decay. So you can imagine it's not a very power-dense fuel at all. If we can speed it up, give it a kick in the butt, then we can open the possibility of a safer, cleaner and cheaper nuclear power design. It's safer because there is no critical state it needs to be to operate. There's no runaway risk at all. Thorium's decay is aneutronic. There's no neutrons that we have to deal with. And it's non-fissionable. And that is the big kicker. Because it's non-fissionable, it's cleaner. We don't have to deal with efficient products. Instead, we have to deal with natural decay products, which turn into those natural products within hours in the best case. In the standard case, it's a matter of under a decade half-life. And it's cheaper. We think that it can be significantly cheaper in terms of CapEx and OpEx. Okay, how is thorium currently used in standard thorium breeder reactor designs? You take your regular thorium that you would dig out of the ground or extract, you smash it with a neutron, and that neutron capture after a period of time will lead you to uranium-233, which is a fissionable isotope. That will then undergo fission. You'll get two products there that hang around typically for a very, very long time, and a bunch of neutrons and an incredible amount of energy, 200 mega electron volts per fission event. Our discovery is twofold. Firstly, we were first to report oxygen cluster emission from a thorium-232 nucleus. For that, we need to have a specific chemical environment, and then we need to induce a specific inner shell electron state for this to occur. This is the one that gives us a 12-hour half-life, and the energy produced through this decay path is on the order of 20 MeV. So just 10% of the fission decay. Where we can make that up, though, is that we believe we can get a high concentration of our design. So in a breeder reactor, you typically don't have those high concentrations of the uranium fissioning. Okay, the second one is that radium-228, the standard, this is the natural decay path of thorium. It will spit out a alpha, which is that helium-4 there, that's energetic. And you'll end up at stable lead-208 after approximately 6 years. The energy is, again, about the same, 20 MeV. So our goal now is to demonstrate control and demonstrate a selective decay. And what this means for us is we're proving out what could be a stepwise change in the nuclear landscape. This could change how it looks in, say, 20 years. If we're successful in doing this, then we can have a solid-state nuclear battery where instead of having a fixed power density, we can now have a throttle on it, and we can dynamically adjust for a required load. So this is all blue sky thinking at this point in time. We're very early in the research, but I wanted to start implanting some of these ideas because the nuclear landscape can drastically change. Okay, this is all happening in real time. So we've spent the last 12 months diligently going through with some of the best detectors in the world in terms of looking at nuclear transitions and the inner shell electrons, so X-ray transitions. We've hung it all on that hyperpower.com site, so you can go and take a look in your own time. But this is fresh off the bench, so this is just last week. We can create the chemical environment needed for low cost. Lithium, bromine, and hydrated thorium nitrate are the basic building blocks to make a what is a super ionic conducting complex that we then irradiate with terahertz irradiation. So my team are probably not going to be stoked with me talking about this, but it's too exciting to not talk about. We can do this. We measure X-ray spectrum before, we measure X-ray spectrum after, and we can confirm that there is extra radium present. This shouldn't be possible, but it is. Okay, really quickly, because I'm running out of time. How does it change? What could a reactor design look like? The design considerations, no neutrons, no fission, but we do have significant gamma still to deal with. So on the right-hand side, we can do the alpha voltaic direct electrical conversion. That's where we take those energetic particles and they punch a whole bunch of electrons, and those electrons is essentially what you use to power everything. More complex, arguably, is a direct substitution into an SMR. Both of these things require lots of thought, lots of planning, and more resources than we can provide. Really quickly, for Africa, I think what a context that would work really well is something like a deep well concept. Deep fission, I know, are doing it in the States, but they're looking at a conventional nuclear. They will put a reactor about a mile down, but their design is limited by pressure. So not being limited by pressure, you can put it just a safe distance down. That way, all of your thorium transport essentially occurs on the surface. You do the catalytic processing above, you drop the active units down to the bottom, and this could be applicable for either the solid-state nuclear battery stack or the SMR substitution as well. The caveat with this is you have a stable geological environment and no aquifers that could be impacted. really quickly because I think I'm running out of time. Costs, we're really early, but basically construction and capital costs make up the most for conventional nuclear today. 20% is operating costs. Of that 20%, the fuel preparation costs are about 15 to 20%. We believe we can get that down drastically to just 10% of that block there. In terms of construction OPEX, it's really too early to say. This is a very, very early stage in this discovery. To finish up, nuclear energy innovation can happen in Africa, and I believe that this is the place. This is the nexus because you have a real incentive and you have enabling resources beginning to flow. Costs can dramatically come down in a mature concept, and safety can dramatically increase. Funding sources, finally, is that traditionally these programs, these research programs belong to strategic government national programs. However, because we have no fission products at all, the non-proliferation aspect goes completely out the window. That opens the door to public-private partnerships to accelerate this transition. We've got a lot of work to do, but we'll do it for the 600 million people on this continent, 250 million people on India, and the rest of the world will benefit. Thanks. Are there any questions? I know I went a bit over time.
Yeah. We have any questions from the audience? I think we have time for one or two of them. There's one. Mike?
We should get you a microphone. Yep.
Thank you very much for the presentation. My name is Kwizera Christian from RAEB. I was curious to know how much energy are we talking about, because you showed the reaction and there's some energy released. For example, you know, in fission there's 200 MeV released, and I wanted to know how much energy for involved in that reaction that you just showed. Thank you.
Yeah, good question. The decay paths for both of those natural decays are on the order of 20 MeV compared to the hundreds that you were talking about, so between 5 and 10% per reaction. Yeah.
All right, there's a second question there.
Thank you very much. My names are Taishimie Fidel from the University of Science and Technology. I'm currently learning in applied physics. So my question is this one. As you presented mainly about the paradigm shift, which I thought it was a shift from traditional nuclear energy to this one that you invented, which will use thorium. My question is simply this one. How can small modular reactors and these microwave modular reactors, really, which we need to use them in Rwanda as well as in Africa in general, how could it boost the energy access and sustainability as well as innovation, as for us we are young Africans who are now building? Thank you very much.
Thank you for the question. What I presented here today is a bold statement of evidentiary fact. What it will take, though, in order to get a paradigm shift is we need to become an integrator of institutions, both academia and aligned researchers, and we need to start to break down some of the models that don't align with what we actually see in experiments. This whole thing takes a long period of time. It's not something that can happen overnight. But what I will say is that we can have a partnership where we bring in those institutions, bring in the academia, and more to the point, I believe that SMRs and this kind of technology can absolutely coexist. It's a rising tide situation to promote both.
All right. Join me in thanking Christopher David Scott, the founder of Exifuse, for his remarks. Now, we live in very exciting times for nuclear. Things are changing more quickly in nuclear now than they have been for the last 50 years. That, of course, means that they're still taking years to change. We still need to improve, but change is in the air. Some of the change is technological, so some of the change is regulatory, some of it is around construction. Join me now in a little fireside chat with Professor Ian Farnan from the University of Cambridge and the director of the Nuclear Energy Centre for the UK for a fireside chat. Right.
Hi. I should just correct you. I'm director of the Cambridge Nuclear Energy Centre, not the UK Nuclear Energy Centre. That's someone else.
All right. Thank you. So I want to talk a bit about nuclear energy, what actually makes it unique. We want to talk about fuel today, about waste, regulation, and construction management. What is nuclear fuel? What makes it so unique?
Well, I think sometimes we lose sight of this in the discussion, but the difference about nuclear energy is the energy density that we have in the fuel. And this has, I think, particular application in this area where you're using small modular reactors or micro reactors, because one of the costs in using electricity is sometimes the transport of that electricity. It's the most expensive way to transport energy. And by having a nuclear fuel that's very energy dense, you can just transport that nuclear fuel. Okay, so you can have more distributed reactors, or you could have micro reactors. So effectively, you remove the necessity, say in the case where you're generating small amounts of, well, reasonably large, but in the order of a few megawatts of energy, you might have to transport enormous amounts of diesel oil to a remote location where that energy is used. Whereas if you take a high energy intensity fuel, you can deliver that once every few years, or with more modern fuels, which are more highly enriched, and we've innovated on fuel performance over 5 decades or so that they can be used for much longer in the reactor. And so you might have a delivery once every 10 years of your fuel. You can imagine the advantages in terms of logistics and those sorts of aspects.
So talking about energy density, we always hear a lot about this unique energy density of nuclear. Could you help contextualize that for the non-technical people in the audience? How dense is nuclear fuel?
Well, the typical sort of argument is that it carries as much energy as sort of a few million tons of coal, for example, right? So that's the sort of paradigm you have to think about. It's that you're changing the way that you're fueling something by basically having it on site, and also because it's going to last for a long time. You've delivered a large amount of fuel in a small volume, or a large amount of energy in a small volume. If you're going to invest in an energy-intensive infrastructure project, such as a factory or a hospital or something like that, if you're working out the costs of that, it's not just the stability of the supply when you need for those manufacturing or medical environments, it's also the stability of the cost. So you're not going to get wild fluctuations in the cost of your fuel because you're going to know the fuel from the beginning. And I think that has, for people here from the investment world, that's a significant message to take on board.
So what about innovations in the fuel? We hear a lot about HALEU and TRISO. How could these technologies help Africa specifically?
Well, I think these innovations are basically, as I mentioned before, the way that the clad of the fuel has been improved, and so it allows fuels to burn up for longer, so we get more energy out of each unit of uranium. And then we can also put more uranium in. But one of the motivations for doing that is when we have something like a TRISO fuel, where there the fuel is actually not contained by a sort of containment building, but actually at the fuel itself. So there's multiple layers of containment around a kernel of uranium dioxide or some other uranium oxycarbide, something like that. Then that's a little sort of involved to fabricate that fuel, so it's a little bit more expensive. So it's advantageous to make that more highly enriched. And that's where it sort of helps in this situation where you've got we don't want to refuel so often, right? And I think that's a big advantage.
Certainly, especially for off-site remote mines, I think it could be very interesting.
Yeah. And one of the advantages, I mean, that I think where there's interest in using small modular reactors or micro reactors in mining is we've had several of the distinguished speakers talk about the distribution of resources, energy resources, mineral resources. One of the determining factors in whether a mineral is exploitable economically is actually how you work out the energy cost. And again, this idea that you have a fixed energy cost because you can deliver all the fuel for a decade in one transport, that's a huge advantage in terms of working out the viability of mineral extraction. It maybe opens up more resources in different countries.
It's very interesting. And then the existing fuel that we have available today, would you say we need those innovations, or what's the performance level of?
I think that's one of the main innovations that there has been in nuclear energy, I think, in terms of is in the fuel performance, the improvement in the fuel performance, and so that we get more energy out, far more energy out than we did, say, 20 or 30 years ago from the fuel.
So the fuel today is already very advanced over many decades of research.
Yeah, and I think that's an important point when we think about, taking on technologies which are new to a region or a continent. A lot of the development and economic pain has already been suffered by the countries that had to pay more for each unit of nuclear energy because of the developments in the fuel.
Now, one thing, of course, is always you buy the fuel, you use the fuel, but then you got to store it, and people call it nuclear waste. How do you deal as your area of research in nuclear waste? What would you say African nations should be aware of when addressing nuclear energy?
Yeah, I knew this question was coming, so I did a few back-of-the-envelope calculations. So Africa uses about 900 terawatt hours of electrical energy at the moment. And if we take the amount of spent fuel that's generated in France, France produces just under 400 terawatt hours of electrical energy a year. So we have about, and that produces about 110 cubic meters of spent fuel. So if we talk for the whole of Africa, we're talking about 250 cubic meters of spent fuel if we generated all the electricity in Africa by nuclear. Now, 250 cubic meters, something which we can't get our heads around, but if we do some simple arithmetic, if we divide that by 2.4 and 2.4, 2.4 meters is the profile of a shipping container. And we get out that we would have somewhere around 3 to 4 shipping containers of nuclear waste for all of the electricity that's being used in Africa today.
So it would take many decades to fill up this room.
Exactly.
With,
you might not exactly space them like that. You need to take into account some criticality issues and some heat generation, because they're still generating heat from decay processes, but the actual volume of the fuel itself is very small. I mean, if you take the example of Rwanda, which uses about 0.9 terawatt hours, I think, the fuel package of 1 year of all of Rwanda's electricity, if it was generated by nuclear, would be about this big, okay, about 25 centimeters on the side.
Right. And I think it's always also worth mentioning that we actually handle this waste stream so well. The civil nuclear energy industry has maintained this waste stream for over 70 years now and never had an incident occur. Nobody got sick because of it, ever. So it is very unique that the nuclear industry is one of probably the only industry in the world who can completely isolate this waste stream from the environment.
Yeah, that's true. And I think it's important to bear in mind, if people are, there's always a lot of talk about nuclear waste problems on various locations around the world. One of those is in the UK, on the Sellafield site, also in the US on the Hanford Reservation. So the Hanford Reservation is purely a military operation, right? So this is where they reprocessed fuel to extract plutonium for military purposes. And that's where you've created a lot of waste, where you've used acids to dissolve up the fuel, and then those acids have degraded the tanks, and you've contaminated the environment. But that's not civil nuclear. And same case in the UK, particularly we had some military applications. We also had some experimental reactors, which created lots of very exotic wastes, and those have caused us some problems to handle. But if you're just handling spent fuel, it's quite a simple problem.
Right. Would you say it's also an option for African nations that don't want to deal with this issue to take advantage of the infrastructure that developed nations are?
Yeah, and I think a lot of vendors and their governments will probably facilitate the take home of the fuel. So, and there is a history of that. So the US took home a lot of the research reactor fuel. We had a mention of that research reactor program, which was started in the 50s, went through the 60s. Those research reactors used highly enriched fuel, so that was taken out as part of a program and all repatriated to the US. So there's precedent for these international arrangements where fuel can be taken back. And to be honest, as I described, the volume of spent fuel that's created is very small. And so the creation of some of the very large sort of infrastructure repositories that we're doing, say, or we're imagining in the UK and are happening in Scandinavia, those sorts of things are not, I don't think, viable because of the scale of the electricity use at the moment and even a fair distance into the future.
Great. So on the technology side, nuclear has really a lot to show for, but we've noticed over the last couple of decades that nuclear is quite expensive on the economic side. Could you tell us maybe why is nuclear so expensive?
Yeah, I mean, at least in the Western world, one of the things I say is that it's not the technology that's expensive, it's the money that's expensive. Okay, so finance costs are somewhere between 50% and 2/3 of the cost when you build a reactor in the Western world. And that's one of the main problems. And then when you so the interest rates are very high. And so one of the solutions to that is to really work hard on the financing. I think there are lots of other discussions that are going to take place here on how we do that. I mean, just think of the situation at Hinkley Point C, which is a UK reactor where very high interest rates are being paid on the project finance for that. And that's going to come in at about $15,000 per kilowatt installed. Whereas the Barakar project, which we've heard a lot about in the Emirates, that's coming in at about 6,000 kilowatts, $6,000 per kilowatt installed. So what's the reason for that? reason for that is that Barakar, in a very broad sense, Barakar can fund it out of a sovereign wealth fund, whereas in UK government insisted that there had to be some external finance for that first sort of new generation of reactors.
And then on the regulatory side, it's always a big discussion in nuclear, what role does regulation play? There's something called ALARA, as low as reasonably achievable, a word that gets thrown around a lot. Could you help our audience understand how has that contributed to nuclear increasing in cost over the many decades since it was actually one of the most competitive energy sources in the 70s?
Yeah, I mean, that's one of the biggest changes is the increasing safety requirements, and associated with that, the sort of paperwork and regulatory compliance work that you have to do to get a plant licensed. And that's a significant cost, but also there's an effect where the ALARA principle means that, you know, as low as reasonably achievable, so that if you make your design more efficient, then there's some headroom for some profit. That seemed to, you know, you could view that as that what happened then was then that wasn't used to make the energy generation more profitable or more economic. It was used to improve the safety. And so a colleague of mine gives a very, salient example is that in the aviation industry, it's a very safe industry. When we get on an airplane, we feel very safe. And if you fly across the Atlantic, say, on a plane, you have 1 in 10 to the 8 chance of dying in that journey. And it costs $500 or something to do that. You could pay $5,000 and have a 1 in 10 to the 9 chance of dying in that. But no one's going to pay the $5,000 to cross the Atlantic like that. That's because it's already safe enough. And in some ways, nuclear, with its improvement over the decades, has become safe enough. And I think that's where we're a very important point. We start to go away from, we're safe enough, and now we can think about all the ways that we can make it more economically beneficial. These are the ways now we try and attack the diseconomies of scale of having smaller reactors by making them modular and made in factories. We try and take control of the costs in the supply chain. So because nuclear is perceived as very risky, supply chain suppliers, they add a contingency to all of their costs. And those contingencies feed through into the final price of the electricity. Now, if you can have either a vertically integrated supply chain or some innovation in the way that the contracting is done in that supply chain so that the risk is shared, then you can also reduce quite a lot of the cost. So a lot of these costs come from a sort of perception, I guess.
So how could African regulators think about adopting a different framework that would allow them to do this? There's the traditional design review process that the Western nation undergo, but they take hundreds of regulators to work that are highly specialized to work for many years. Many African nations won't have that capability for many years to come as they build out their knowledge base. So how could we build a regulatory framework that would allow African nations to implement nuclear that is safe enough and also take into account all the benefits that nuclear generates so that the hundreds of thousands of people in Africa who still die of air pollution because they breathe in the smoke that they have in their houses because they cannot afford to cook with electricity? How do we implement a system that balances both the benefits of cheap energy while also incentivizing safety?
Yeah, I think this is one of the really key areas, whether we can come to some international agreements to approve each other's regulatory approvals, okay, so that there would still be some oversight by sovereign nations, but that there's be an agreement amongst nations in terms of their regulation. And this is already happening. I think there's already collaborations between various regulators. UK and US and Canada have some sort of, progressing regulatory agreements. These types of arrangements, I think, are going to have to happen because each country in Africa can't have, as you say, the same regulatory infrastructure as a country like the United States. That's not going to work. So we have to be innovative in how we think about that, but still maintain the safety. And I think that is possible.
Certainly. There's a big need to work together across the continent, across the world. But also we should not be doing the same mistake that a lot of that collaboration has led to in the past, where it's just you add another layer on top. You don't only have to comply with the US regulation, you also have to comply with the UK and then with France, and then you have to have so many different requirements. So somehow build a regulatory framework. But that's probably a much longer discussion.
Yeah.
So let's talk actually about modules and small modular reactors. What do they bring to the table? What's the innovation here that could address this cost question that nuclear has been struggling with?
Well, I mean, there is a reason why people build bigger and bigger reactors, and that's economies of scale. So there are diseconomies of scale. As you make a reactor smaller, the price of electricity is going to go up. But you have to try and then recover those diseconomies of scale somewhere. So some of the costs in building large reactors are that they're built entirely on a site, or almost all on stick-built on a site. So those ways of building are not going to be relevant to small modular reactors. They're going to be largely built in factories. Components could also be tested in factories. So this is also part of regulatory innovation that we were talking about just slightly earlier, is where do you do the regulation? Sometimes it might have to be in a factory to ensure that you've passed particular tests. And so the advantage of that as well is that if you look at innovation advances across all sorts of industries, construction industry is one of the poorest performers in terms of innovation. One of the highest performers is in manufacturing. So you move your manufacturing of the reactor components and the reactors themselves, perhaps you construct an entire reactor in a factory, into a realm where the possibility of innovation is largely increased.
Doesn't that create some risks for African nations, as most of these factories would probably be in industrialized nations that have large experience with manufacturing, to be left out of that and not utilize that large construction workforce that we have here on the continent?
Yeah, I concede that could be an issue. You'd like to think that there could be some, if you like, some sort of assembly type of role in Africa for some of that production. I mean, the other thing as well is that the very stringent controls on the materials of a reactor are one of the issues, right? You have to have nuclear grade or all sorts of things. Largely they're to do with pressure. So it could be if you move to low pressure systems, then you reduce the engineering controls that you need to, you no longer have to deal with the fact that your system's going to be under very high pressure. So I think there are ways around this, and I think it's one of the most important issues about using nuclear energy in Africa is whether it's going to be can it be a native sovereign technology? Well, parts of it can, I think, but it may be that it's an enabling technology, as we've heard people saying. We need to do more house building. We need to build more factories. Is it just an enabling tool for that? So that might be the way to counterbalance that.
All right, that brings us to the end of our time. Thank Dr. Ian Farnan